The Lewis dot structure of a molecule is very important to chemists because from the Lewis dot structure, we can then figure out what is the shape of the molecule, which has a lot of implications on what it will do. The shape of the molecule is determined by the electrons around an atom. You look at the central atom and you look to see how many groups of electrons that you have, and those groups of electrons all have negative charge and try to get as far away from each other as possible. And so from numbering the groups around an atom, you can determine what geometry it has. A group is either going to be a bond to an atom, and that can be a single bond, a double bond, or a triple bond is all one group, or a lone pair of electrons. Let's look at an example here. Here is the Lewis dot structure for carbon dioxide. Notice the central atom, carbon, has two groups on it. A double bond here and a double bond here. That's two groups, not four groups. It has four bonds, but two groups. Two groups of electrons in the bond are going to repel each other and try and spread out in space as much as possible. And what they end up doing is having a 180-degree angle. When we draw the molecule, we find out that the atoms are all in a line. So we call the geometry of carbon linear, and the whole molecule we say is linear, but the geometry around the carbon is linear with 180-degree angles. Notice a double bond and a single bond both are one group apiece. If I look at oxygen here, just to show you, for example, how many groups are on it? Well, three, because it has 1, 2, 3 areas, 2 non-bonding pairs, and then a double bond. So that's 3 groups. Let's look at the next example. Here is formaldehyde. It has how many groups around it? A double bond to oxygen, a single bond to hydrogen, and a single bond to hydrogen. That is 3 groups. 3 groups or areas of electrons spread out in 3 dimensions to 120-degree angles. If you look at the atoms, you can see hydrogen, hydrogen, oxygen. They form points of a triangle around the carbon. So we call this shape around the carbon, the electron geometry, we call it trigonal planar. And we say the molecule is trigonal planar. What does that give you? 120-degree angles between each set of electrons. Notice 1, 2, 3 groups. If you have 4 groups, those things spread out to 109.5-degree angles. Notice many students want to take 4 groups and put it around in at corners of a square. It's what we call square planar, because they want to draw it on a flat paper. But we live in 3 dimensions. And for 4 things to try and get as far away from each other around a central atom, it goes into what we call a tetrahedral shape. The angle's 109.5, and this is very symmetrical. Those 4 points are at the quarter of what we call a tetrahedron. So the carbon we say is tetrahedral, and then we also say the molecule is tetrahedral. You can have 4 groups, but with one of them a non-bonding pair. See, look at this Lewis dot structure. 1, 2, 3, and then the 4th group is a non-bonding pair. It's tetrahedral also. The electrons are tetrahedral about this nitrogen, but one corner of the tetrahedron is a non-bonding pair. If we just look at the atoms, the 3 hydrogens and then the nitrogen, the nitrogen's kind of up in the middle of this pyramid, and the hydrogens are at the corner, and what it makes the molecule kind of pyramidal. See that there's hydrogens down here that it's resting on, and the nitrogen is up between them. The angles are close to 109.5. Here's water. Oxygen in the water has 1, 2, 3, 4 groups. They also the electrons go into this tetrahedral shape, but because we're only looking at the atoms, all we see is this bent molecule because the non-bonding pairs are at the corners of that tetrahedron. If you're not seeing this, just wait until we get to class, and in class I will have models for you to look at. The summary of the molecular shape is that two atoms attached to a central atom with no non-bonding pairs, that's linear. Three atoms attached to a central atom, what happens is it becomes trigonal planar. Four atoms attached to a central atom, that's tetrahedral. Three atoms and one non-bonding pair, or two atoms and two non-bonding pairs, give you tetrahedral geometry for the electrons, but the molecular shape is trigonal pyramidal with the one non-bonding pair, and bent for two non-bonding pairs. So now go ahead and try. What is the molecular geometry for each of these? And we're talking about the central atom, so only look at the central atom. Okay, if I look at this molecule, you'll see there's a phosphorus with 3 bonds and a non-bonding pair. The electrons are tetrahedral, but the non-bonding pair at the corner of a tetrahedron gives the molecule trigonal pyramidal shape. Here you have 4 bonds around the carbon, so it's tetrahedral. Oops, let's go to this one. This one you have 2 bonds, they're double bonds, but 2 bonds around the carbon, so that gives a linear shape. Here, tetrahedral. And here you have 1, 2, 3 bonds around the sulfur. One of them is a double bond, though. And what do we get? We get trigonal planar. All of these bonds do not have necessarily perfect sharing. This imperfect sharing causes electrons to shift to atoms that are more up and to the left. And we call the shifting or the pulling of electrons in a bond onto an atom electronegativity. So for instance, if I have a hydrogen bound to a fluorine, because hydrogen is a nonmetal and fluorine is a nonmetal, that will be a covalent bond. But because the fluorine is more electronegative, what happens? See, it has a value of 4 versus 2.1. The electrons are shifted onto the fluorine, and there's a slight negative charge on the fluorine and a slight positive charge on the hydrogen. You need to know the trend in the periodic table, which is up and over, increases electronegativity, and that hydrogen is less polar than any nonmetal except for phosphorus, and is equal to phosphorus. As for the metals, you don't have to worry about the electronegativity. We're only going to use electronegativity with the nonmetals. Okay, when we look at electronegativity, it's saying how much the electrons are drawn on a particular atom. So if I look at this carbon-carbon bond, they have the same electronegativity, so they share it equally, and there's no shifting of the electrons. However, if I look at an atom with 2 different atoms, there's potential for an electronegativity difference. And if you look at carbon as 2.5 and hydrogen 2.1, there's a slight shift in the electrons moving to the carbon. Now, what we do with carbon-hydrogen bonds is we usually ignore it. Not only is it's a small difference, but there's usually a lot of symmetry around the carbon that cancels out any small electronegativity difference. When you have atoms with different electronegativity, we have a shift in the electron density, and it goes onto one atom more than on the other. For instance, if I look back at that table, you would see that oxygen has a value of 3.5 for electronegativity and carbon 2.5. That means oxygen is going to pull the electrons onto itself more than the carbon. So it builds up a small amount of negative charge that we write as this symbol here, del. It's a lowercase delta, negative. And that also, pulling the electrons away from the carbon, leaves a small positive charge, which we write as del positive. This is what we call a polar bond, and it's due to a difference in electronegativity. Now, those numbers you don't have to memorize, because you will be able to figure out which one's more electronegative by the trend in the periodic table. Carbon is to the left of oxygen, so it's less electronegative. Oxygen is closer to fluorine, the most electronegative element, so it pulls the electrons. So the atom that is closest to fluorine ends up getting a del negative. So the key things to know about this is the electrons are not shared equally. The atom that is closest to fluorine gets a del negative. The atom farthest away gets a del positive. And there's a slight there's a shift, there's charge there. It's a small amount, but it's charge. And because there is a separation of charge, positive from negative, we call it a polar bond. If the electronegativities are the same, then we call it a nonpolar bond. So if the atoms are very far apart on the periodic table, for instance, metals with nonmetals, we consider it to be ionic. But if the atoms are close together and they are carbon-oxygen, carbon-nitrogen, oxygen-hydrogen, or nitrogen-hydrogen, they are covalent, but they're considered to be very polar. If you have them in both nonmetals and they're not, these bonds are still polar, but it's only slightly polar. For instance, carbon to a sulfur is a polar bond, but it's only slightly polar. If the atoms are both nonmetals, the bond and they have the same electronegativity, we call it nonpolar. If they're the same atoms, or if you have carbon, hydrogen. So, molecules, because the individual bonds can be polar, molecules can be polar. There's a way of drawing the molecule in 3 dimensions and putting in the dipoles and seeing if you see a positive side and a negative side. But a really quick way of figuring out if a molecule is polar or not is just to look at the Lewis dot structure and look for symmetry. If you have all the atoms on the outside being the same, and there are no non-bonding pairs on that central atom, notice it's the central atom, then it's going to be nonpolar. But if the central atom has a non-bonding pair, or if the atoms on the outside of that central atom are different, well, then it's going to be polar. Let's look at some examples. Look at this carbon. There's no non-bonding pairs on the central atom, but the atoms on the outside are different. It's polar. Look at this molecule. There's no non-bonding pair on the central atom, and the atoms on the outside are the same. Nonpolar. Here, the central atom has a non-bonding pair, so it's polar. Here, the atoms on the outside are different. Polar. So you determine, are any of these molecules polar? Well, if I look at this, this has a non-bonding pair on the central atom, so it's polar. If I look at this, there's no non-bonding pairs on the central atom, and the atoms on the outside are the same, so it's nonpolar. If I look at this, no non-bonding pairs on the central atom, and the atoms on the outside are the same, nonpolar. If I look at this, no non-bonding pairs on the central atom, and the atoms on the outside are the same. It doesn't matter that this one has a double bond and that's a single bond. It's still nonpolar.